Hi everybody, and welcome back to our next lecture on projectile motion, where we're still dealing with our monkey problem. So as you recall, we have a monkey high up in a tree, hanging by a branch, and we are somewhere down below, far away, and the moment we fire the gun, the monkey is going to let go of the branch and drop to the ground. So we've been trying to figure out where to aim. Do we aim somewhere above the monkey, somewhere straight at the monkey, or somewhere below the monkey? Now you'll notice that where before we talked about firing something horizontally, and we know we had to aim at the monkey if we were at the same height, now we're down below the monkey and we're firing at an angle. So what do? Well, this situation is known as an angled launch. And that is because you're firing something with an initial velocity at some sort of angle. And again, we're right back to dealing with the idea of vectors. And whenever we have a number with an angle, a vector with an angle, the first thing we really need to do is to break it up into its components, both the horizontal part of it and the vertical part of it. And we do this using our simple rules. Y goes with sine, x goes with cosine, number, function, angle. So in other words, if I want the velocity in the y direction that I fire this, in other words the upward velocity, I take that velocity times the sine of the angle, and that tells me how fast it shot upward. Then if I want the horizontal version of the velocity, I take that number times the cosine of the angle, and that's how fast it's going horizontally or forward. Again, separating them out into their two parts, because remember, they are independent of each other. Next, we then apply our acceleration rules in each direction. And we all know now that once something is fired in the air, the only acceleration it feels or undergoes is gravity. And gravity only acts one direction, straight down. So that means there is still no acceleration in the horizontal, and all the acceleration is in the vertical, gravity, negative 10 meters per second squared. So let's look at an example. Once again, we've got our cannon out here, and we're going to stick another friend in here. And this friend we're going to fire out of our cannon at a wonderful speed of, say, 100 meters per second, with the cannon set at an angle of 30 degrees with the ground. Now, to be nice to this friend, we're going to allow a net for her somewhere. So, a little circus act here. And, of course, the path she's going to follow is going to be a parabola, an arc. Now, I'm sure a couple things our friend might want to know. First of all, how much time will she spend in the air? I'm sure it'd be very important to know what the horizontal displacement is so that we know where to place the net. And finally, what is the maximum height? What is the maximum height she will reach? Okay, so let's start with our chart. Once again, what we want to do is separate out our vertical and horizontal motion in terms of all those things that we've been talking about: initial velocity, acceleration, time, displacement, and final velocity. And let's go with what we know. Now, the one thing we always know right away is acceleration. Negative 10 in the y, 0 on the x. Always true no matter what the situation is. Now, the trick is we don't really have other numbers to put in here, with the exception of 1. You see, she's launched from basically near the ground and lands near the ground. So in other words, vertically, she has a displacement of 0. In a way, she goes straight up and comes right back down to the same point. So that's another number we know, but that's all we can fill in right now. Now, we have this 100 meters per second and 30 degrees. That is the entire initial velocity of the person we've launched. So let's break them up into their components. First of all, the y component would be the velocity times the sine of the angle. So 100 sine 30, which is 50 meters per second. Make sure your calculator is in degrees. The x component is the initial cosine of the angle, or 100 cosine 30, which is 86.6 meters per second. Now, what I can do with those numbers, I can put them in my chart. 50 goes in the y, 86.6 goes in the x. Now, on that x direction, something we already figured out before. If the acceleration is 0, the velocity is constant. So that means the initial and final velocity are the same. But now we have one other neat little trick in this example. Because she's launched from the ground and lands on the ground, in other words, has a displacement of 0, well, this would be the same thing as if we shot her straight up in the air at 50, which means she would have to return to the same spot at negative 50, kind of like just throwing a ball straight up and down. Whatever velocity you go up, you have to return to the same one. Now, looks like it's going to be very easy to find time in the y column because it's the only thing that's missing. And it allows us to use our favorite little simple equation, final velocity equals initial plus acceleration times time. Now, again, we can only use the numbers in the y column because that's where we're trying to find time. No using x numbers. So I have negative 50 equals positive 50 plus negative 10t. I subtract 50 from both sides, negative 100. Divide through by negative 10. Remember, not allowed to get negative time. And so that means she spends a total of 10 seconds in the air. And once again, 10 seconds is the number that time is allowed to cross both sides of the chart. That can't change. But now that we know the time in the x direction, we can get that horizontal displacement. And that's just our good old displacement equation. Now, we want a horizontal displacement, can only use horizontal numbers in the x column. So initial velocity 86.6, time of 10 seconds, and the acceleration is 0, giving you 866 meters. So a little over half a mile. It's a long way to go. Not too bad, right? Now, the last part though, maximum height. Height is a vertical direction. And there are a couple different ways you can approach this. One of the best ways is saying, well, she's going to go up and come straight back down to the same position. So if it was 10 seconds for the full ride, it must be 5 seconds to get to the maximum height. Okay? That's one way to do it. It's not my favorite way, though. And sometimes you aren't launched from the same height. But we do know all the time that if we reach a maximum height and turn around, before we can do that, we need to stop. In other words, I'm going to have a vertical velocity of 0 at that point. So since I don't want to use time, I'm going to use time unknown. So Vf squared equals Vo squared plus 2ax. Now, maximum height is in the vertical direction, therefore I can only use numbers in the y column, in the vertical. But my final velocity up there, the maximum height is going to be 0 because I stop and turn around. The initial in the y direction is 50. Acceleration in the y is negative 10. And then I'm looking for that displacement. 50 squared is 2,500. 2 times negative 10 is negative 20. Subtract 2,500 and divide by negative 20 because I should get a positive displacement because going up in the air. And I get 125 meters of height. So again, what we see is sort of that independent nature of horizontal and vertical information. But the one thing that sticks through any example we have here is that acceleration. that the only acceleration is in the vertical, and the only acceleration is -10, gravity. So that brings us back to our monkey. What do we do? Well, the one thing that we definitely know through all of this projectile motion is that the only acceleration, once the shot is fired and once the monkey lets go of the tree, is due to gravity. And gravity only acts one way, straight down, and they both undergo the same acceleration. So if they both always undergo the same acceleration, let's change the number for a second. Let's dial the acceleration down to 0. Now, if there was no acceleration and the monkey let go of the tree, he'd just hang there. He would just float, wouldn't go up, down, just be at rest, because there would be nothing to accelerate him downward. And if we fire anything in the upward direction with no acceleration, it will have to travel not in a parabola, but in a straight line. So knowing that the monkey would simply stay still, we know we would have to aim straight at the monkey, because the bullet would travel in a straight line and the monkey would remain floating there, and therefore they would intersect. Now, if I switch on gravity for both of them, well, the monkey begins to fall, but then the parabolic nature of the bullet causes it to also go in that arc and fall at the same rate. So that means that at the same time, they will have come down to the same distance. So the answer is, we still must aim at the monkey. And that's because both objects undergo the exact same acceleration, that of gravity. Now, if the monkey, of course, knew we were aiming at him, shouldn't let go. Or, if we knew the monkey wasn't going to let go of the tree, we would clearly have to aim above him, because then it would have to arc back down onto him. So there you have it. You ever have this dilemma with the monkey? You know how to aim at him. Now, to prove it, let's watch this video of this demonstration. Okay, so the way the shoot the monkey experiment works is that there is a gun right here, and way up there is a monkey hanging from a tree. Now really that monkey is my boss, Mr. King. He's a history teacher, so basically a trained monkey. Is hooked to an electromagnet that is then linked to the photo gate on this launcher here. So the moment that something breaks the plane of the photo gate, the monkey lets go of the tree, so that hopefully they will both happen at the same time. As soon as the shot is fired, the monkey will let go of the tree. Okay, now we're ready to do the experiment, and the idea is that we need to aim the gun directly at the monkey. Okay, so I've kind of got a laser here showing that the gun is lined up directly with the monkey. And the reason it has to be at is because when the gun is fired, as soon as the ball leaves the gun, the only thing affecting it will be gravity. But that's the same thing that affects the monkey as it drops from the tree, gravity. And as long as the gun is aimed at the monkey, both will fall at the same rate and should meet somewhere in the middle. Now, let's watch. And as you can see, the gun was able to hit the monkey in mid-flight, because they both intersected at the same point because they both fell at the same rate. Let's watch that again, this time in slow motion. Okay, that's all on projectile motion. See you next time. Bye.